Hi there. On the bench today we have a Yaesu FT-1000MP amateur transceiver. Now this Yaesu FT-1000 has a little bit of a story behind it. It's been to some other techs before it's got here, and that means that the failure points within this radio are no longer virgin failure points. And what I mean by that is when you have a virgin failure point, that means that something has gone wrong in the radio, and usually it's only isolated to one section. You very rarely get two completely separate problems failing at the same time. So when other techs get in there and they can't fix the radio, there's a really large chance that he slipped with a probe or not connected something right or just caused more problems. And I'll give you an example with this radio here in just a second. So most of the time I tell people, no, I'm not going to bother with it because it's just way too incredibly time consuming, and a lot of the times you end up, by the time it gets to your bench, it's a charcoal briquette, and you really don't want to fool with that. The catch-22 here is the fella that brought it here is a fellow ham radio operator, and he's also a very good friend, so I always have time for my friends. So I said, okay, bring it over, let's put it on the bench and I'll check it out. And, well, here it is. So, he said that the last fellow that owned this thing, he says that he checked the final sections to see if the final was good, and he bridged a bunch of stuff out inside the radio, and the radio put out full power. Okay, well, that to me is just, red flags. There's a reason that this thing isn't transmitting. It's not putting out any RF power. Usually, when the receive is low and there's no RF output, usually there's something either open or shorted in the final area or on the front end of the radio, and there's sensing circuits inside these radios that shut them down so that they can't put out RF power, so that they'll damage the finals or do anything like that. These radios are actually pretty complex inside, and they sense all this stuff. So if the radio is creating high standing waves or something internal to itself, it'll shut off. It won't do anything. So by this last fella bridging this section out and making this thing transmit when it's really not supposed to be transmitting, again, could have caused a lot more problems. So we might have two completely separate problems to chase down now. Now I'm hoping not. I'm hoping that everything just went smoothly and that the original failure points are still there and nothing else has happened. Now, if I remember correctly, this has been here for a little while now because I haven't had much time to fool with this thing, but it's now made it to the bench here, and I'm sure he's probably pretty happy because he's been waiting for this for a while. But the original complaint was the receive was slowly dying off, and so was the RF output. The RF output was kind of going down with the receive, and I think in the end, when he ended up bringing this to this other fella, it had very low receive and no RF output. So hopefully these are still kind of the same issues in here. But what we'll do is we'll go through this together, and we'll make sure that all the original failure points are the original failure points, and I'll look through my notes and make sure that nothing has been added to this so that I don't have to chase down any other points, even though if it has, I guess I'm still chasing them down because, as I say, he's a good friend. So let's tear this thing down together like in the other videos and go through this piece by piece and fix this FT-1000 and make it happy again. We're now ready to do the initial power on test with this Yaesu FT-1000MP. What we're looking for in this initial power on test is to make sure that we don't have any additional failure points added to the original ones. And the original failure point in this radio was low receive and no RF output. So before we turn this radio on, we want to make sure that a couple of buttons and dials are in the right position. So we want to make sure that the MOX and the VOX buttons are both out. We want to make sure that the RF power is down. And we should probably turn the audio gain down for both the main and the sub, so that just in case this thing makes some horrible noise, we don't scare us out of our chair here. And, just the rest of the knobs, kind of common sense, centered, no attenuation, AGC on auto or slow or wherever. We want this to be in receive mode when we actually turn this on. So if it does go right into transmit mode, chances are I'm going to shut it off right away. Antenna A on the back of the radio is connected to a dummy load inside of my transmitter test set. So if this thing does go right into transmit mode and, full throttle, put power out, this will show it right away, and of course I'll be shutting it off. And of course we're not looking for that. We want this to be in receive mode. So I'm going to turn this thing on. Everything is about in its right position. I'm going to keep my finger on the power switch, and watch my transmitter monitor and make sure that everything on the display is going to be a really quick test. If I see something crazy, I'll shut it right off, and if it looks like it's somewhat behaving, I'll just leave it on. So here we go. And everything looks normal. It's on antenna A. We don't see transmit. We have no transmit power, so already we're off to a good start. So let's see if we got any static. And we do. So it's trying to receive. So we're not in transmit mode. That's a good thing. We are in AM right now. And as I say, it's on antenna A. Let's see if the sub works, if this guy's going to work over here. Yeah, it has audio gain too. So there's a couple controls that are trying to work. Whether they do or not at this point, we have no idea. But it's kind of behaving. So we're in AM right now. We can try and see if this will put out any kind of RF power. So the RF power is right down at the bottom. I'll push the MOX and keep a close eye on this and on the power scale here. I want to make sure that it's on collector current so I can monitor the collector current of the output transistors. And I will throw it into manually operated transmit mode right now. And we don't have any power output, no collector current, no power there, but it is in transmit mode and the receive section went quiet, so there is switching going on. I'll try and turn the RF power up, and we have absolutely nothing there. So I'll turn the MOX off. Let's try FM. Okay, turn the volume down here just a little bit. Turn it back on again. And absolutely nothing out. So pretty much safe to say that it's making no output power whatsoever. So go back into AM mode here. So now let's test the receive out. So we're at 3.707. So I'll just turn my fluke counter, or my fluke signal generator to 3.707 megahertz here. 3.707 megahertz. I've got 10 microvolts coming out of my signal gen, so I'll take this off of the test set, the piece of coax over here, and I'll put this into my signal generator at the top. And it looks like it's trying to receive. I'll put a tone on it for a sec. Yeah, it's trying to receive. So that's on antenna A. So let's try, if I move this to antenna B, it should go quiet. And it's not. There is no change between antenna A and antenna B, which right there indicates an issue. So I'll unhook the signal gen from antenna A. I'll screw my adapter onto antenna B, and we'll see if antenna B switches. Okay, I'm on B now. So B seems to be switching, but antenna A seems to be jammed. So that kind of indicates that there may be a stuck aperture inside of a relay back here somewhere, or some relay isn't turning on, or it hasn't been put back together properly. So we have a bunch of things that it could be. So I am on the antenna B port. Let's take this off the signal generator and put this back into the dummy here and see if it will transmit on antenna B. Wouldn't that be something? B here now. We are on B. Yep. RF power's down to nothing. AM, MOX, transmit mode, and nothing there either. Well, that was wishful thinking anyways. So, well, we know that the receive is switching on B but not on A, so right now we already have a direction to go in, because it should go quiet when we turn it to B and it's on antenna A. So to me it's already sounding like there's a switching problem with some relays or something like that back there. So at least we have a place to go. It is trying to receive, and which is a very good thing, so we're off to a really good start so far. It's just that we have no RF output. So on to the next step. We'll take the lid off and look at some of the switching and try and locate this issue, see if it's just been put back together bad, or whether it's actually something faulty back there. Here we are inside the top of this Yaesu FT-1000MP, and I immediately noticed this relay in the back here has a hole pushed right through the top of it. So I imagine that's why we're not getting our antenna switching action. And notice that there's a big solder glob right there. I removed this one little RF jack so you could kind of see on here too. So it's just been thrown back together. So that looks like a hole. It's actually been melted with a soldering iron or something. I can see the movement of the relay inside. So I imagine that the plastic is probably jamming the movement. So that obviously needs to get replaced. So what I'm going to do is I'll probably cut the top of this relay off just to stop that from jamming the movement while I test this, and then move on to the next issue. And then of course when I find all the issues, then I'll order up some parts. Another thing I noticed immediately is I noticed a squirrel cage fan here. Hear that? It's binding on a black wire in here. So whoever threw this back together didn't check anything out. If that fan would have started up, it would have augured through that black wire almost immediately. I think that's the only thing it's binding on. It could be binding on one of the end caps here or something too. I really don't know. And this is a pure example of what you get when you're dealing with non-virgin failures. This is a product of somebody else, and so is this. So now I have to fix these extra two things also. So there's just a pure example. It makes you wonder what else is haywire in here. I see lots of scratching on the wires. When I remove the screws out of the case, you can tell that they've got lots of miles on them. You can see in the tops of them, some of them are stripped. So these screws have been in and out of the case a lot. So it makes you wonder how many times this has actually been apart. So there's just a couple of things, just right from opening the lid. It's immediately saw that, because of course I'm looking by the jacks on the back of the radio. So there you have it. So hopefully that's all of the damage that I find in here. I'm hoping that none of this is there is no more damage above and beyond this point. So when I have some more to show, I'll be back. Okay, I've removed the squirrel cage blower here, and it seems to move pretty freely. And it was rubbing on this black wire here. Just trying to auger a hole through this. Another nice little thing I've seen here is, look at this screw. It's threaded in sideways, and that's tight. It's this thing was just absolutely thrown back together. Get that flash there, the light over here, so that it'll focus on it. There you go. So you can see how it's just threaded in completely sideways. So it looks like all the wiring down here, there's tie downs and stuff that are supposed to hold the wires in place, and these are just sticking straight up, so they've been bent straight, so nothing's been put back together properly. The wires that are supposed to be in these clips are not in these clips. The clips have been delatched. That's the reason that these wires are rubbing, is because they're supposed to be, inside here like so, and then this is supposed to be clipped back together. So it was really just thrown back together. So I have a feeling that the person that threw this back together had a feeling this wouldn't never work anymore, and it was just going to be a parts radio. So I really don't know the story behind this, but it's pretty rough. So I'm going to remove the RF module right now and take a look underneath, and hopefully I don't see any more scary things. Here we are with the RF module upside down. It's just loosened off. So you can see here, it's probably good that this thing actually didn't turn on. You can see this the screw, how loose that is. It's not even tight. It's just, it's just completely loose. So, things have really been botched back together here in a very, very quick way. So it's a really good thing that this hasn't, actually powered on. I was expecting this thing to actually be put back together properly, but I'm imagining this whole thing is just, loosely threaded back together at this point. So what I'm going to do is open up this cap and check it out inside, and I'll come back with some more. Here we are in the final amplifier unit and the low-pass filter unit inside this Yaesu FT-1000MP. And immediately after opening the case, I notice there's a wire just floating in mid-air here. It's hanging there, so I guess that's probably connecting into this socket over here. It just keeps getting better. So now, this is a row of relays in the low-pass filter unit, and this is another row of relays, and then there's two over here. And what I usually do, kind of normal protocols, I'll remove all these relays carefully because this is a single-sided board that has no plated through holes. You got to be very careful that you don't lift traces or anything like that. And of course you need the proper tools to do that. And it's a Heiko 470 over here, and I've got the 802 head down here. It's kind of dark because I've got all my light focused on the radio here. So I'll remove all these relays and test all of them, and I'll test them on this device right here. If you look for my relay testing video, look for this little picture but with a green cross in the center of it, and you'll see how I test relays. So I'll end up doing that there, and we'll get into the amplifier unit here. So we'll look in the amp here, and this is where it gets really good. I'll get my light down here. You can see he's lifted the base lead of this transistor here, and he's trying to, I guess, do a gross failure test on these transistors or something like that. You really can't test these properly this way. You need to put them on a curve tracer or test them in circuit. Even the diode test for 2SC2879s doesn't yield very good results. They'll test good on the diode test, but they'll make 1 watt. So they're just, you really need to remove these and test them. He hasn't removed any of the emitter or collector leads on this. He just lifted the base lead, and it's just kind of tacked down roughly. So I imagine that is probably just wanted to see if they're shorted. But there's an easier way of doing that. Pretty much just test to see if there's any voltage on these two, the positive and negative terminal, the main power coming in. And if there's no voltage there, chances are they were shorted and it blew a fuse in the power supply, or it's shutting the power supply down. So that's really, this is an unneeded test. You test them in service. So we can see here there's a thermistor up here for some purpose. Usually thermistors are for fans in these amplifiers. I'm not sure. I haven't looked at the schematic yet, but you can see it's not even touching the case of the transistor. It's just kind of in midair, so that thermistor is doing nothing. This diode is still connected to the case with the thermal goo, so that's okay. We look over here. Now this one I lifted just before I did this video to see what the number of that transistor is down there. Kind of get an idea of what's going on. You can see this thermal goo made no contact to the case. See the case of the transistor? There's absolutely no thermal goo on it. When I lifted it, there was no contact. So this is actually a diode here. So this is another, temperature sensing unit they used to shut it down with. So that diode was really not doing nothing. This looks like an NPN-PNP pair to me. I recognize these numbers. These are found in CB radios. Look at, I'm putting heatsink goop on it already. I'm getting ready for it to be put back into service here from poking that thing. There's goop on the end of my tool here. So they look like an NPN-PNP pair or something like that. Probably a preamplifier section in here or something. There's another one over here. I'm not sure of this one's function, and it has a diode that is, this one I haven't touched, and it's just kind of floating here. There's no goop under it. So the topology of these amps is usually quite simple. The RF comes in here, and we can kind of see it says TXN, so that's really no rocket science down there, TXN. And it comes through a preamp section, and then it goes into this. This is the base transformer for the 2SC2879s, and it comes out of this big transformer, runs out this piece of coax, and goes into this little jack here in the low-pass filter board. So that's usually how these work. You can see that he's opened these two leads here. Now this looks like this is in line with the transformer here, so I imagine this is to set the idle current in the power amplifier. And there's only one VR in here, so that VR is most likely setting the idle current for these transistors here, but I'll look on the schematic and verify that in the end. If I'm leading you astray at all, I will correct this with notes in the end, but I think it's pretty straightforward. So you see there's a piece of wire just kind of tacked in here and laying across the terminals like this. It's just, I don't know what's going on there, just craziness. So there's a whole bunch of crazy things going on inside this amplifier, and make sure that I've kind of looked at everything in here. You can see that these have been removed, these two RF transistors, and they've just been, kind of soldered back in, and nothing's been cleaned off or anything. So I'll have to either retest all of these or see how they work in service. It's always a bad idea to leave resin or flux around the leads because little solder balls and such can get caught between leads, and then when you least expect it, they kind of roll when the circuit board gets hot and it shorts things out. So you have to really clean all that stuff off. This one here looks like it's been removed and just tacked back into the spot there. I'll move this little thing here. You can see it's just been tacked back in. So it's there's a lot of work to be done in here. So lots of scary stuff. So this unit here, I'm going to have to completely remove this and check under the board and see if there's any damage there or anything like that. And of course this board will come right out because I have to replace, or not replace, but check all the relays and replace the ones that are possibly faulty if there are any. So my next thing is this thing receives, and we put it into transmit mode, and there is no transmit. So what's happening here is this lead is where the RF drive comes in into this board. It says TX in. My camera will focus here. So what I'll do is I'll probe this lead, or find where this lead exits on the board and probe this and see if there's any RF drive here. And how I'll do that is I'll put it into transmit mode, and I'll turn this RF power control up and down right here, RF power control. And I should see a varying amplitude and a signal coming out here at the frequency that's listed on the display. And if there's varying amplitude and a nice clean drive signal here, we can pretty much be assured that it's either something to do with this amplifier or some form of switching. Something isn't being turned on up here for some reason. So that's where I'm at this point, and the next step will be to probe that to see if there's any RF there or whatever, because as I say, we have no transmit. It seems like it's trying to receive, but just no RF out. So I'll get this all set up and we'll look at that next. We're now at the point to where we're going to start to troubleshoot this radio. And as I mentioned earlier, we're going to see if there's any RF drive coming up through this cable, and the easiest place to check that is the base lead of this 2SC2166. So this is a schematic for that amplifier. And if we look over here, it says TX RF. This is where that RF signal is coming in. That's that little jack with the orange cable in the back here. So it goes through this little transformer assembly and through a 0.047 microfarad cap into the base of the 2166. And that's where we have the scope probe lead tied off to. So I only have two hands here, so I have to kind of pre-plan this before I do this. So this is clipped on, and we're all ready to look to see if we have some RF drive at this point. The radio's on, so what I'm going to do is push the manual operated transmit, and I'm going to variate the RF power control down here, and we'll see if we have any variation in amplitude on the scope. So here we go. There's our RF signal, and I can variate it. I'll turn it down here. I'll turn it back up. So at this point, we know that we do have RF drive coming into this 2SC2166. So now the next logical place to look would be on the actual collector here and see if we have a larger signal here, because there should be amplification here. And there is nothing there on the collector. Okay, I've already been there with the scope lead, and there is absolutely nothing there. In fact, there is no DC voltage there at all either. So if we have no DC voltage here, this isn't going to work. So if we follow this down through here, we find out that we end up here, and there is a switch down here. We can follow this right over to here, and there's a voltage that runs in here, comes along here, down here, over into this switch. So if we look down here, this little jack controls this switching circuit, and that just so happens to be this wire here that's unhooked. And that's what's supposed to be hooked up into this jack here in order to tell this amplifier to turn on. Now, we need a positive signal on here. If we look, we see we have an NPN transistor here, so we need a positive at this T switch, at the T terminal here, to turn this on. And when this turns on, through this 1K resistor, it pulls the base lead of this PNP transistor low and allows the voltage to go through this transistor and up into this area, of course going up into this area and into this collector of this transistor. And it also feeds a regulator here, which of course is regulated because this sets the bias. There's a bias set down here for the final power transistors, which happens to be that VR that I mentioned earlier. So in order to see if this works, we actually need to measure the voltage here. Now I'm not going to try and turn this thing on at all, but I'm going to measure it, and if there is no voltage here, that's going to tell us that we need to start tracing back in the circuit and see why there is no voltage on this and why this thing isn't turning on. This resistor here is just a pull-up resistor because there's voltage on this line, and what happens is, in order to stop this transistor from accidentally turning on, there's a 10K pull-up there which keeps the voltage on the base high, and then there's a 1K underneath it which allows this signal to override that 10K resistor, and of course this transistor here will pull the base low and turn this on. So this is just basically to stop that transistor from false firing. So the next thing we're going to do is I'll plug that in and I'll see if there's any voltage at that pin 2 there, and if there isn't, we're going to have to start tracing back down inside the rest of this unit and find out where that goes. We're now going to look for some voltages in the RF power amplifier. So the main power comes up through this red wire here, and that supplies this RF power amplifier with voltage. Now this is around between the 12 and 14 volt range usually is what's up in this wire here. So we'll probe that and make sure that that's there first. That red wire is the main power for this entire unit here. So I'll look up at the voltmeter here, and yeah, we have 14 volts. So that's okay. So the second thing that we're going to do is check this little connector here again. This connector is what tells this amplifier whether to turn on or not. So this is basically the transmit signal comes up through here. Now if we look again at the schematic, what we just tested on the schematic is the voltage at this point here. This is the main positive supply. So it runs along this rail and down through here and waits at this transistor for the signal to go positive on T. And when we have a positive voltage on T, it turns this transistor on, and then it allows the voltage to pass and power up the various areas of this power amplifier. So now, one thing that's really odd about this whole thing is that this connector here with these two wires, the red wire is the ground wire, and the white wire is what carries the positive signal. I swear they do this stuff on purpose. So I'll poke my probe in here. We'll look up at the voltmeter and I'll put it into MOX mode, and we have no change. So I'll take it out of MOX mode. So now we're thinking, uh-oh, we have no signal up here to tell this amplifier to turn on. Before we get too crazy and start searching through this entire radio, when this radio came here, you see this little blue switch right here? If you open the door up on the top of your FT-1000MP, there's a little switch, and underneath that door it's blue, and if it's pushed towards the back, it'll disable the power amplifier, in effect stopping the voltage from going up through that cable. It actually breaks that white wire in these two connectors here. Okay, so you need to make sure that this is forward like this, so that way the wire basically can come through one connector and go right out the next. So what we'll do now is we'll look back at that white wire in the back here. Okay, I'll put my probe back in there again, make sure that the RF power is down right at the bottom. That's on the face of the radio. We'll look up here, and I'll put it into transmit mode, push the MOX button, and there we have our voltage. So you can see it's varying quite wildly. It's very unstable. Okay, and if I move my probe over to the actual main supply voltage, it's quite stable. So this is telling me that there's some voltage instability coming from another board in this radio. That's really jumping around. So I'll turn the RF power up here and see if we get any RF power. That's full RF power right there. It's about 2 watts. The radio is actually sitting at 3.8 megahertz, so it's pretty close. So you can see it's at 5 watts, 4. You can see the modulation levels jumping all over the place here. And you see the powers moving up and down. So it really doesn't know what it wants to do. So most likely the reason that this is doing this is there's very slight variation in the drive level right now. So I'll take it out of MOX mode. So let the radio rest here. So what's happening is the voltage is coming up to this little white wire here from a board on the bottom. This basically is derived from an IC on the control board. And the voltage that's coming out of that IC must be varying in order to be varying up at this point, because it's basically a direct connection all the way through the switch, unless we have a bad switch or a bad wire somewhere. But by me actually seeing the wattage bobbing up and down like that, that pretty much tells me that the actual, I'll just zoom out here, tells me that the actual power supply is varying. So we have enough voltage here. It's staying around the 5 volt range, and that's enough to keep this transistor on. So we should have a stable voltage at this side of the transistor, because as I say, this is supplying this with enough current to keep this PNP transistor switched in right now. And what I'll do is I'll put my probe on the collector of that transistor, and I'll see if I can put it into MOX mode here. Move my lamp out of the way. So now we're on the collector. I'll turn it into MOX, and you can see how stable that voltage is, because that voltage is just reflected from the main supply voltage from that 14 volt supply that we saw, and that drop we're seeing is because it's going through a transistor right now. So I'll turn this off. So this is, the transistor switched on. That's the voltage that's actually getting to that 2SC2166 in the corner that we were probing with the oscilloscope earlier. That's on the collector of that transistor. But yet, the actual switch voltage is doing this. So that tells us that there is enough current there to keep that transistor in, and it's pretty solid. And the voltage drop is correct. You usually have around 0.6 of a volt drop through a transistor. So the voltage on the white wire is varying wildly, yet the collector current of the driver transistor over here, or the collector voltage of the driver transistor, is very stable. So this little switch transistor here, I'll see if I can zoom into it a little bit. Camera's on a funny angle here. This little transistor here, you can just see the head of it. This transistor is staying on even though that this is varying. Again, this is pointing towards another board and some power supply instability. I imagine that maybe even with that, the drive power might be varying just a little bit coming up into this amplifier. That's probably what's causing all of this. And of course the drive level is probably low and varying because we're only getting 2, maybe 3 watts, sometimes 5. It just depends on what it feels like at that point. So the next thing we're going to do is we're going to look at some of the power supply areas and find out where the actual signal's coming from on the control board and probe that area and chase our way back to the problem. We're now on the bottom side of this Yaesu FT-1000MP, and this is the control board that we're looking at here right now. This board here is what does a lot of the critical thinking inside this radio. Now this IC here is what is basically doing all the controlling, and it's sending signals out into this Q5014, which is a decoder IC, and that decoder IC sends a signal out of pin 15 and pin 14 to tell this radio to either go into receive or transmit mode. Now those two little traces that come out of pin 15 and pin 14 come out of a lot of these ribbon cables and just random connectors here. So it comes out of the connector that's just underneath this one here. It comes out of this wire loom here, which is another connector. It comes out of this ribbon cable here, goes into this board, goes through this ribbon cable into this board, and it basically goes just all over the whole radio, goes onto the upper side and everything. So there's a lot of places in here that the signal could get screwed up if there is an actual problem with cabling or on the circuit board. Now one thing I have to do, admit that is kind of frustrating about working on these designs is that when Yaesu labeled these boards, there is no correlation between the numbers on these boards that's listed here. And that's really just kind of stupid. So you can see here it says J5016 is this connector, but we have that connecting to J2014 on a different board. We have J5019 here connecting to J2013. It would have been a lot better if they would have had J5019 connecting to JA5019 and J5016 connecting to JA5016. But no, they have to have this ridiculous numbering system on the actual boards to have this interconnect and stuff like that. Now, they're nice enough to put IF here and IF and AF and AF, and they tell you which boards are which by that. You pretty much align the connectors here. But when you're looking at the schematic, it really does make things difficult. Now they have a really long number underneath that you can correlate that's way longer than this number, but there's no need for any of that. Just do it all in one number. It's very simple. We don't have 5,016 connectors on these boards here, so you could start with connector number 1 and go to connector number A1. It would be very simple. Anyways, this kind of stuff always gets on my nerves in these radios. There's no rhyme or reason for that. That's just completely stupid. At any rate, so here we have, that's my rant for the day, by the way. So this is Q5014 here, and pin 15 and pin 14 are the pins that those signals come out of. So now pin 15 is the transmit pin, so if we keep an eye on the voltmeter over here, I'll put my finger on the MOX, which is the manual operated transmit mode. I'll have to steady my hand here. I don't know if I'm going to block the voltmeter that way. I'll steady it over here instead. Okay, and I'll put it into transmit mode. And there we go. And we can see that the voltage is varying right at that pin. It's varying quite wildly, so I'll put it back into receive mode. So that transmit pin goes low when you're in receive mode, and of course the receive pin is going to go high. There we go, the receive pin's high. And it's varying just standing there. So we know that the actual signals that are coming right out of this decoder IC are varying at that point. So the next logical place to look would be at the supply voltage for this IC. And the supply voltage, if I grab the piece of paper here, the supply is pin 9 and pin 10 is ground. So pin 9 on this IC here is the supply, and you can see there's a little cap across it to keep any RF and garbage off it. And we can see this one is ground. So let's probe pin 9 of this IC. And we can see that the supply voltage is varying all over the place. It's 8.674. So the supply voltage is moving. So the next thing that we're going to do is we're going to trace down the actual supply and find out why the supply for this decoder IC, and probably a lot of the ICs on this board, are moving around. Let's see, we have some 74HC logic here. So the standard protocol for the voltages on 74HC logic ICs is pin 7 is ground and pin 14 is positive. So let's go to pin 14. And there's the 5 volt supply there, and that's dead stable, 5.01, and that's right within tolerance. So that's absolutely fine. So the 5 volt supply is really stable in here. So now the supply for that area, I believe, is probably the 9 volt supply. So what I'm going to do is look that up, and I'll be back. Here we are back on the top side of the Yaesu FT-1000 again, and I've removed another shield in here, and we're another layer deep. This here is the regulator board, and this supplies all the voltages to all the various parts of this radio. So if you recall, on the bottom side of the board we were looking at that decoder IC, and the main supply for that IC was fluctuating, and that's a 9 volt supply. So this is the schematic right here for this regulator board, and you see we have a 9 volt supply here. Lamp up here. We have a 9 volt supply here, a 5 volt supply here. These are just standard linear regulators. There's a 13 volt supply here, which comes out of this main box up here in the front. That's the main power supply for this whole radio. And then we have a DC to DC converter, which is in a little shielded box that creates our negative 9 volts that runs out. And that's pretty much what comes out of this little regulator board. So these two linear supplies are bolted right to the side here of the radio, and this one here is the 9 volt supply. So what we're going to do is turn the radio on and probe that supply and see what kind of voltage we get on it. So here we go, radio's back on. And I will probe that pin. And we can see it's moving around up here pretty crazy too. Now that's right at the regulator output. So let's go to the input. Get my probe on that pin there. There we go. And it's stable. No problems at all. And then of course the output pin again. It's moving all over the place. So that's supposed to be 9 volts. So now this could be a problem in that actual regulator itself, or it could be a problem on another board. One of the other boards might have an intermittent short, or something that's just trying to short out, or something that's just randomly pulling a little bit too much current. Now when we turn the volume up on this unit, you hear that cracking and that popping in the speaker. It's pretty pronounced. It's really loud right there. So that kind of leads me towards the AF unit. Just for a chance, what we'll do is we'll disconnect the actual AF unit and we'll look in there. So the AF unit itself has two connectors. There's one connector here, J9010 and J9004. So what we'll do is we'll unplug both of these connectors, which will completely cut the power to that unit and maybe even some power to other pieces of the radio, because there is daisy chaining connectors all through here. So what I'll do is I'll shut the radio off again. I'm going to unplug the radio before I disconnect these connectors, because these are the connectors down in here, and we have a 120 volt AC supply here, and you don't want to come across that. So this connector up here is J9004. So we'll disconnect this connector here. And J9010 is this one back here with the blue wire. We'll just disconnect that. So now we're not going to have any audio or anything. So I'll plug the radio back in, turn the radio on, display still lights up normally, and of course we have no audio. That's full audio right there. Now I'll probe the positive pin of this regulator again, and we'll check out the voltmeter. And that's pretty much rock stable. So now these connectors daisy chain through this radio and go all over the place. So this radio really is the king of daisy chaining connectors. So there might be other connectors on that board that are connecting to even more boards, and they might even, who knows if they're almost making a full circle here. So what we need to do is go onto the bottom side of the board again, and of course find this corresponding connector. Again, of course, they'd have no, they don't have a proper legend for these connectors, so I'm going to have to look for this connector, see where it enters, and find its appropriate corresponding number on the other board. And then at that point we'll be able to look on the schematic and follow the schematic and see where that 9 volt line goes. And if it goes to any other boards, what we want to do first is we want to disconnect all the other boards, and we just want to narrow it down to one board. So the 9 volts does go out in all sorts of different connectors here to other boards, but this is just one board. So far we're at that board, and if it's daisy chained to others, as I say, we're just going to try and isolate it down to one board. And that's what we'll do next. Here we are back in the bottom side of the radio again, and I'm on the audio board. I've disconnected this ribbon cable that goes over here to the IF section, just for the reasons being that the 9 volts comes out of here and goes into this board here, and I don't want it to leave this board. I want to just see what's happening in this board. And you can see we still have a pretty wildly varying voltage here. It's 8.2 volts. It's been up to 8.7, 8.8. See, it jumped up to 8.4 there, 8.5. So it's still moving all over the place. So the problem seems like it may be within this board here. According to the schematic, this is the only cable that the 9 volt comes out of this board and then runs into this board here. And that, as you see, has been disconnected. That's just kind of floating here like this. So this is where we're at. We're down to 8.1 right now. So it looks like the problem could be here, and that's what we're going to focus on now, is this board right here. What I've done now is I've removed this connector from the audio board here, and this pin here, this one that's in my alligator clip here, came out of this connector here. So what I've done is I've removed that from the connector with a small screwdriver. You stick a jeweler's screwdriver under these tabs here. I'll see if I can come in just a bit closer. You can see these little tabs here. If you lift these little tabs, try and find my jeweler's screwdriver. What you do is you just lift these little tabs just a little bit. If you lift it too far, you'll actually snap the tab off. You don't want to actually snap these tabs off because they're what hold this in. There's a little kind of like a dimple in here that locks this little connector in here. What I did do then is I plugged this back in. This is the 9 volt supply wire right here, okay? And then what I did is I hooked my current meter in line with it. So I'll just plug this back in here, like so. And then I hooked my current meter right here in line with it. Okay. So I got to hook this green lead back up to here. And this is just basically running this through my current meter. And then I'll put this in this little slot here. And now I can read the current to this board. So I can see that it's only drawing 325 milliamps or thereabouts. Now what I did also do, which I couldn't do on camera, but I also added a varying load to this, and I watched the voltage on my other meter on the top there, and I loaded this lead down. This lead goes right to that 9-volt regulator. So when I got to a certain point, and then all of a sudden it just stopped and it went right back up to close to 9 volts, and it's staying there now. So what that tells me now is that the actual regulator on the top is the intermittent part, because now that it's been loaded at this point down here, we can see it's a steady 324 milliamps right now, right? Just barely moving whatsoever. That last digit means absolutely nothing there. And if we look up at the voltage here now, after I've loaded the unit, I'll just probe the voltage at the terminal here, 8.85 volts. And it hasn't moved. It's just dead on now. It's not moving at all. It's really stable. It's actually looking really good at this point. And that was from loading that regulator. Once I put a little bit of a load on it, a little more than it was used to, it made the regulator act somewhat normal again. So at this point, we can pretty much say that the regulator itself is intermittent. I'll just shut the radio off here. So we can pretty much say at this point that regulator is acting intermittent, and it needs to be replaced. So we'll go and replace that regulator, and on to the next problem. Hopefully this is it though. We're now back on the top side of the Yaesu FT-1000, and I need to remove this regulator board to get this regulator out. So in order to remove this board, I need to take out this screw here. This one here looks like it just holds this heatsink on. And there's another one back here that holds the heatsink on, and then there's one more I've got to remove here that attaches this board here to the chassis. Now they're hiding one of the screws under the shield here, so in order to get this board off, I need to unsolder this glob here. That's the DC to DC converter box. And I also need to desolder over down in here. They've soldered it to the adjacent shield on this box here, not on this particular box, but on the box that goes around this. So they have a glob here, and a glob here soldering it on, because DC to DC converters are just horribly noisy, so they're doing all this to try and get rid of that hash from the receiver. So once I desolder all that and then take out this screw down here, I'll remove all the wires, and there's one extra screw on the back side here where my finger is, just below right here, and that should allow me to remove this regulator board and replace this 7809 linear regulator. So once I've got this board out and I'm working on the board, I'll be back. Okay, just a quick note here. There is a little bit of an easier way to get this shield off. You still have to desolder it from the top of this box, but if you just remove the screws on this adjacent board's shield, the entire shield will just come off, so you don't have to actually desolder this from the side here. You don't need to desolder this from this. So that makes things a little bit easier. You just have to go after this one little spot. Now that I've got all the wiring looms removed and that shield removed, we can get a little bit of a closer look at the board here. So in order to get this board out, we need to remove this screw here, this screw here. This holds the heatsink on. We can leave this alone. Leave this one alone, remove this one here, and remove this one over here. Disconnect all of these wiring looms here, disconnect these here, all these wires across here, this one here, and then this little guy down in the corner, and of course the AC supply. And you're pretty much in at that point. So now what we're going to do is get rid of this little troublemaker right here. This is the regulator board out of the Yaesu FT-1000, and this component here is the offending component. This is a linear regulator. The part number of this piece is KIA 7809. This is the 5-volt linear regulator here. It's an HA17805. You'll notice that we have two different style packages here. One's a TO220 style, just a standard TO220, and this is a TO220F package, or sometimes known as the isowatt package. Now this package has a coating of epoxy over the entire package, so you don't need to use a mica spacer behind it, and it makes it quicker for quick runs on assembly lines. They can put clips on these things and just clip them to the heatsink really quick, and you don't have to worry about the placement of a mica spacer. Well, these are both 78 series linear regulators, which means that this is ground. The actual tab is ground, so it makes no sense for them to have an isolated regulator on this actual heatsink surface. So the center pin of this regulator is ground. On all 78 series regulators like this, the center pin is ground. And the center pin on this 7809, or KIA 7809, is ground also. And this jumper right here that you see that little jumper right there, is just joining the grounds. So we've got this, grounded here. The center pin's ground. It goes through this jumper here over to here and attaches to this ground here, and then just goes over to the ground that's on the heatsink tab here. And also it's grounded to the chassis of the radio right here. So why they're using an isolated component makes no sense. Now, it doesn't look like it's been changed or anything. The resin is the same kind of burn color as it is on here, and around these little pieces right here we can see some resin. It's all that kind of a dark brown color. And it doesn't look like the board's been out, because when I resoldered the actual adjacent fence around the other circuit board, this spot doesn't look like it was actually tampered with or anything. It looks like the original solder spot. So the manual calls for an L7809, and this here is an L7809, and you can see that it has an exposed metal heatsink tab, and that's what's going to go back in. So somebody might be being really tricky and cleaned up their work and put this particular F-style package in here. That might be the reason it failed, because the thermal conductivity of this package isn't as good as the thermal conductivity in this package, because we have an exposed metal surface on the back side of this package, whereas this has to transfer heat through a thin layer of epoxy to this surface right here, which of course creates a little bit more, as I say, thermal resistance. So by having an exposed metal piece on a piece of metal here with some new thermal paste, and when this gets installed back into the radio, we're obviously going to put some thermal paste on this so it'll transfer the heat right into the chassis of the radio. Hopefully this will make this regulator board last a really, really long time. This regulator under here is a DC to DC converter, which is a switching power supply, and it makes lots of hash and noise, and that's the reason that they've put it in this box, and they have a separate RF ground here. And this is a DC ground and an RF ground, and of course it's soldered to the adjacent fence. So this negative supply here is the negative supply for the 9 volts, and this is the positive supply for the 9 volts here. And that's pretty much that little regulator board and what's going to get done. The regulator board is now done and ready to be reinstalled in the radio. You can see the new 7809 here. It's been tightened down and there's thermal compound behind it. What I usually do is I clean off the excess thermal compound that's just kind of squished out when you tighten the part down. Just clean it off with a Q-tip. I also retighten the screws that hold the heatsink onto the board, because over time these screws do get loose. And even the screw that holds down this 7805 has been cinched up a little bit. So they're all nice and tight right now. From heating and cooling and from the radio being moved around and all that kind of stuff, the screws do tend to back off a little bit. These tabs here are where all the main wires from the power supply get tightened onto, and the screw tension, there's quite a bit of it there, so when you're undoing these and retightening the screws, sometimes there's a chance that you'll loosen up the joints on the back side of the board a little bit, and it's the same with all the little pins in these little connectors. So it's just good practice to resolder all of these. So I've resoldered all of these, and all the pins on these connectors here have all been resoldered. And there's another big connector here which goes to the amplifier. It's been resoldered. And don't forget to clean off the excess resin when you're done, and make sure that you have no solder bridges or little solder balls bridging anything on the back side of the board. And you're pretty much ready to go. So this board is finished and ready to get reinstalled back in the radio. The regulator board is installed in the radio again and is working very well. There's some thermal compound between the heatsink and the case, and it's working very well. It's getting just gently warm. There's a lot more transfer to the case. I can really feel that now. As I say, just gently warm. Nothing's loomed. Nothing is put back together yet because we're still in test mode. You also have to remember before you put these things back together to lift all these tabs up again, so when you put the actual brackets back in, they make good RF connection. So you got to make sure that these are all bent up nice. A lot of the times they kind of get squished down. So that's working good. Right now in the signal generator we got 3.8 megahertz at 3 microvolts coming out, and that's running into the receive section here. And we can see that we've got 3 S units for 3 microvolts at 3.8 megahertz. That's working very, very well. Now what we'll do is I'll remove my coaxial cable here, And I'll put it onto the transmitter test set. I'll shut this light off. Try and get a decent angle here. That's quite a bit of reflection there. Hi. Alright, it's in CW mode right now, and I'll put it in MOX mode. Make sure the RF power is down. Alright, look at our frequency accuracy on the top there. That's pretty good. Alright, I'll turn the wattage up, take note of the power. 100 watts. Right on the nose, that's maximum RF power. It's 100 watts. That was with this RF right to the top. Now we'll look at the scale here. Right on 100 watts. Right accurate. What you would expect for a radio of this caliber. So it's working very, very well. Take it out of transmit mode. 3.8 megahertz right on the button. So the radio is finally starting to come back to life here again. Still, the amplifier has to be cleaned up. I haven't cleaned up the soldering in the amplifier yet and all that. And we'll have to address this board here. This board is a little bit of a sore spot. So this relay also gets very warm at that continuous power, and I don't like that. So that'll be the next project. It's getting closer. This is the factory antenna board in this Yaesu FT-1000. We can see the relay here, and this is the one that's missing because it was had a hole in it, it was damaged, so I didn't put it back in because we just did those measurements. And this is the little port that powers the board up. Pretty simple. We got ground, we have the signal, which is either high or low, and we have the 13 volts positive, which supplies the voltage for the coils to actuate or not. And the relay logic on this board is really simple. They're both on or they're both off. And how that's determined is if this pin goes high, you know, if the control board sends a high signal to this pin right here, both relays get told to get turned on, and they use the 13 volts here to turn them on. And if this goes low, it lets off, and both these relays return to their off state. So when these relays are both in their off state, antenna B is grounded, and antenna A is connected to this jack. When they're both in their on state, okay, antenna A is grounded, and B is connected to this jack. Pretty simple. And that's how this really operates. There's a little coil here to keep RF from going back into the jack. They've labeled this coil at 100 microhenries, which is incorrect. This coil is 1 microhenry, 1.4 actually. So anyways, I thought that was kind of odd. That does not look like 100 microhenry, so I had to measure it. But unless they're, you know, figure what kind of witchery are they doing here, something that I haven't seen before, but sure enough, nowhere near. So this is a diode here, basically just snubbing for the coil here, and you know, to keep the as the actual aperture inside the coil lets off, it creates a voltage spike, and this little diode just stops it from attacking the transistor. There's a little cap across here to keep RF off the diode and out of the coil here, and it's the same thing for this, exact same thing for this relay. So we look on the other side of the board here, we can see the track for the RF. The RF comes here, center conductor goes into this relay, and over here into this relay, unequal lengths. Not quite sure why they're doing that. Doesn't really make sense to me. We see that both of the jacks that run out to the antenna are, you know, this one's longer than this one too, so this is a much longer path here to the antenna than this one. So I should actually probably stick this relay here in this port and retry it and see what the SWR is, just for giggles, because this is a much, you know, there's a lot less lead on here going out to here. So at higher frequencies, actually antenna A may be more affected by SWR. Not quite sure at this point. For giggles, I might just move this over here and try it again. So this is the switch transistor here. This switching transistor is basically just receiving a signal from the center pin here, runs right into the base. This is 2 RF decoupling caps taking RF off the base and the collector lead of this transistor. The emitter is just grounded. So very simple. We'll look at the schematic here in a second. I removed this cap here in order to test this inductor because what they rated it was a little bit eyebrow raising there. And that's pretty much this board. So the whole idea is to make this a little bit more resilient to high SWR, because you got to remember, if you're transmitting, you're doing CW, before the antenna actually tunes the radio, it sees high SWR, this does anyways, for a very brief period of time until it tunes the whole system. So, you know, these are pretty small. They're rated at 2, maybe 3 amps maximum, and you got to realize that, you know, you're firing 100, 150 watts of power into this relay. You know, on at least on sideband, there's quite a bit of pulsed power there, and then it'll put 100 watts of carrier out through this little teeny relay here, and at high SWR conditions, that sometimes will weld, you know, contacts together. And I've heard that there's this board is a little bit of a sore spot. So what we're going to do is take that teeny little relay and use these relays instead. Much larger device, as you can see, and contacts rated at 10 amps. So a much better relay, much larger. So the whole idea is to make these relays work and maintain low SWR on this board right out to the actual jack. So what we're going to do is actually make strip line on this board and have it go right to the jack. Instead of having open free air jumpers like this, we'll actually design it like it should be designed and have strip line running right to the jack. And this is close to the SO239 as we can get it without having free air jumpers. They didn't even put the extra grounds on this board, so I guess why they figured they didn't need it. Maybe that's the reason that this board is a bit of a sore spot. So that's what we're going to do next. In just a second here, I'll grab the schematic and we'll look at the schematic. This is the antenna unit schematic, or antenna switchboard schematic in your Yaesu FT-1000. This board is located right behind the two antenna jacks on the rear of the radio, and these are both SO239s, and this is what that little board looks like right here. There's one relay missing. So these are both relays here, and this is the little switching transistor that's on the bottom side of the board. You can't see it from looking at the top side of the board. And this is the jack that controls all of that. This is marked ANT, but no antenna is connected here. This is the jack that goes into the radio, and these are the antenna jacks here. And this is how this board works. So when you turn your radio on, 13 volts is applied to pin 3 here all the time. It goes through this inductor and into the positive side of both of these relays. Both these relays are hooked in parallel, so they both turn on at the same time and they both turn off at the same time. Both the negative sides of these relays are both also tied together, and they go to the collector of this transistor. So if AN2 goes positive, say you've selected antenna B, this will go positive. It turns this transistor on, actuating both of these relays. If AN2 goes low, say you've selected antenna A again, there's no voltage at this point now, the transistor turns off and both of these relays return to their normally closed state. So now, these capacitors here are to take RF off the collector, and this capacitor is here to take RF off the base of the transistor so that it doesn't affect this and cause it to false fire or do something crazy. These diodes are here to suppress the spike when the magnetic field collapses on these relays. So when this transistor turns off, the field collapses and this sends a spike out. This diode suppresses that spike so that it doesn't affect this transistor and cause the transistor to fail. These capacitors are also here for RF purposes. They're both across each one. Technically they only needed one snubber diode, but they have two here. This one here is, they're both hooked in parallel, right? So you only really need one diode. But for some odd reason, they're running two. The caps would both need to be here to keep, to be across the coils for RF reasons. So they've drawn these relays in a really confusing manner, and I don't agree with this particular drawing of a relay whatsoever. Just more unneeded confusion again. Never at any time do both of the contacts touch each other, and or all three of them in this case look like they're touching each other. That's not how the relay works. But I'll try and explain this as easy as I can. So if you picture a normal relay contact, picture this finger as the black contact, picture this finger here as the white contact, and picture this center as the actual arm, okay? So when the relays aren't actuated, they're in the normally closed position, which is this lever is touching the black arrow right now. So there's no voltage on this board whatsoever. So really, this lever here is touching the black arrow right now on both relays. Okay, when you apply voltage to the relay, the lever does this to the white arrow. So never at any time do these ever touch, because these are the contacts, they're fixed, right? The lever moves back and forth between the two. So the coil is not energized, the coil is energized. That's how it works. So when it's not energized, the lever touches the black contact. So we're going to say that this isn't energized right now, there's no voltage on this board. So if we were to transmit a signal, what would happen is the signal will go down this line, up here, into this black contact. The lever would be touching the black contact, so it goes out antenna A. We would also notice that the signal goes down here into this relay, but there's no connection here because this is touching the black contact. So antenna B is grounded. So in effect, right now with no power on the board, antenna A is connected to here and antenna B is connected to ground. So now, say we put a positive voltage on AN2 and there's 13 volts here. If we put a positive voltage on AN2, this transistor turns on, pulling both the negative sides of these relays towards ground or within 0.6 of a volt of ground, because the transistor here will only pull it down to 0.6 of a volt, okay, or around that anyways, without getting into the theory of transistors right now. So say it's on, so what'll happen now is the RF will come down here, go down here, and it'll go through the white contact, because the white contact is now touching the arm, right? Because the arm's up at the white contact. And it goes out antenna B. And if we look at here, the arm is also touching the white contact right now, so antenna A is grounded. So all it's really doing is just switching like this, and of course the antenna port that's not being used is tied to ground, and that's how they've set this schematic up, and this how this little board here works. So it's relatively simple. So the board that we're going to design and try to improve the dependability of this section of the radio will use larger relays, and they'll have to work on a little bit of a different premise. So what's going to happen here is one relay will be on and one will be off, and then when you hit antenna B, the other one will do that. So it'll go back and forth. So there'll always be one relay energized in this circuit. And I'll get into explaining how that's going to work here quite shortly. This is the new antenna switching circuit for the Yaesu FT-1000. Now it's only this little piece right here, nothing behind my hand is included. This is from an old video. This is my doing math with fire video in response to applied science there. But this is the only area we're going to focus on here, so pardon the mess behind. As I need more breadboard, I kind of strip parts off and they go back into their drawers and stuff like that. So what's my excuse? I'll say too many projects, too little time. Yeah, I'll stick with that. So this is the area right here. A little bit more complex than the factory circuit. The factory circuit uses only one transistor. This uses three, and that's because the relay action has changed. What I'm going to do is I'm going to try and take you through the entire journey of my thought process in designing this antenna board. So there's going to be a little bit of RF work in here and stuff like that too. So we're dealing with DC voltages, and we're also dealing with impedance. We're dealing with things called standing waves. We're dealing with inductance. We'll talk a little bit about strip line and stuff like that. I'll try and keep this brief, but I'll include the most amount of information that I can. If I forgot something, forgive me. Please just include something in the comments if you have a question about anything, and I'll try and answer it to the best of my ability. So the switching action of this has changed now. In the factory Yaesu circuit, both relays come in when you select antenna B, and then both relay coils let off when you select antenna A. And their switching action is a little bit different. Now, I've chosen a bit different switching action just because of the relays, their size, and the way that they work, and dealing with the internal structure and the makeup of the relay. And I'll get into explaining that here in the near future. It's just let's focus on this little area first. So this is reverse logic also, just to confuse matters a little bit more, and that also has to do with the relay structure. So this is the relay B coil, and this is the relay A coil. Now relay B is also the antenna B port, and relay A coil is also the antenna A port. Okay, so when I turn the Yaesu FT-1000 on, of course it will remember what relay is selected, or what antenna port, I should say, what antenna port is selected before you turn the radio off. So say it just defaults to antenna A. So if it defaults to antenna A, the antenna relay B coil will come on. And what happens is when the relay is on, it's grounding that antenna port. So it kind of works in the opposite way. So if you've selected antenna A, antenna B relay comes on and grounds the antenna B port, and the antenna A path will be through. If you select antenna B, the antenna A port will be grounded, and the B will let the signal through. And that's how it works. Now that's a little bit confusing because it's a bit backwards, but that's to do with the way that the relay is made, and I'll explain the thought process, and that involves me dissecting one of my relays. Now the relays that I'm using are these ones here. They're pretty large relays. The contact rating is 8 amps in the normally closed position, so that's when the relay's at rest. And in the normally open position, it's 10 amps. That's when the relay's pulled in. There's a little bit more contact pressure when the relay's in because you have a magnet holding the two contacts together, so the contact, the amperage rating is up a little higher. But you're just dealing with spring tension when it's in the normally closed position. That is the relaxed position, so that's when the contact is just let off. So the contact rating is a little bit lower. They're the same contacts, it's just that there's more contact pressure when the relay is applied. So that's how that works. So this is an 8 amp replacement for a 2 amp relay that was in there. So this will deal with you know, standing waves a lot better, and the relay stays quite a bit cooler. And there's a whole bunch of ups to using a larger relay in the circuit, and that's the reason that we're changing this. I understand from a few people that that board is a real sore spot, so why not get rid of it and make this thing dependable? So that's the whole idea of this circuit. So now, again, in the factory circuit, I'll just explain this quickly again. Pardon the horrible lamp. I'm working under my microscope here. The other bench is full of taken apart Yaesu FT-1000. It's strewn all over the place. So I'm kind of reduced to this little area. I'm dealing with a space about this much under my microscope here to display everything. So I'll try and make this as good as I can here. So AN2 here. AN2 is where the signal comes in from the control board. So if you select antenna B, AN2 goes to 4.9, or you can just call it 5 volts, logic level 5 volts. If you select antenna A, this goes low to 0 volts. So if you select antenna B, this turns this transistor on and both relays come in. If you select antenna A, this transistor shuts off and both relays let off. One quick note, you'll notice inside this transistor here, we have a 10K resistor and a 47K resistor. So the 47K resistor just keeps this transistor off if AN2 floats. And of course the 10K resistor is just in line with the base here for current limiting purposes. So they've mislabeled this L8701 inductor here. This is to keep RF off the 13 volt line. It was rated at 100 microhenries, you can see here. It's actually 1.4. I measured it because it looked a little odd. There's no way that one loop through a ferrite bead could make 100 microhenries. So sure enough, it's 1.4. So I don't know if they made a mistake in their manual or in their writing here or something like that, but I don't know if I mentioned that earlier. I may have. I'm doing this in parts here, so I might be repeating some short things here. So that's how this factory system works. Now, this circuit here works a bit different. Only one relay's in at the time, like I explained earlier. And I'll show you the power supply I'm using here. This power supply up here is hanging on the bottom of my tech scopes here. This is the 13 volt supply supplied to the radio. So when you turn the radio on, this is basically what goes all over the radio, that 13 volt supply. This is the 5 volt supply, and that mimics the signal coming up from that IC on the control board that tells this circuit to do its state change. Okay, so there's very little current required to change the state of this switching action here. It takes about 500 microamps, or around that. I think it's 450 microamps to make this change. So we're dealing with under 0.5 of a milliamp. So it's very, very light, and it will also change state right down to about 0.8 of a volt. And this will switch back and forth. Now if you want it, this is a BC807 transistor, this is a PNP transistor, and these are two BC817s. I prefer using these over the 2N3904, 3906 complement, or the 2N2222, 2907 complement, just because these are really, I've got lots of them, first of all. I got 4,000 of each of them. And the BC807 is a really sensitive transistor. It's a nice transistor. In this circuit, if I use a 2N3906 in this circuit, it takes about 400 to 500 microamps to turn it on, whereas this only takes 100 microamps. And that allows me to do some resistance changes in this circuit here. I'm using 1206 parts on the circuit board that I'm going to build for this. So obviously the wattage values of the resistors matter. This one here would have to be up around 1K or so with everything that I've chosen here if I want to use a 2N3906. And of course this is going to dissipate some heat at that point. And this is a 1/4 watt. So now I can go down to 2.7K, and it's the 1/4 watt resistor basically dissipates no heat. Of course, there's a lot of math involved. You can work out the wattages and stuff, or you can actually keep this pretty simple and just use common sense when you're designing this kind of stuff. If you've designed a lot of transistor circuitry, a lot of this stuff just comes naturally, you know, just what to place where and all this kind of stuff. And if you feel a resistor getting warm, that means that it's dissipating wattage. So, you know, you can measure the current in line with that resistor and work out the wattage, or, you know, measure the drop, or whatever you want to do to measure the actual wattage of the resistor needed. If a 1/4 watt resistor stays dead cold to the touch, I know I'm going to be absolutely fine with a 1206 part. Now, when I design something, I design it to last. I don't want anything to be on the verge. I don't want warm parts. So when I design stuff, as I say, I like to design it and not see it again. So when this is finished, I expect never to see this circuit again, aside from if something else in the radio's design itself goes wrong. So that's a really good ideal to carry around when you're designing something, because, you know, of course, when you design something, you just want it to be dependable. You don't want it to fail. Unfortunately, manufacturers don't think the same way, because there's bean counters in there, and the bean counters, they limit all of the you know, the expenditures, so they're scrimping and saving on every little component. I don't have to do that, so I can overbuild things, and that's just the way that I do things. Hence, you know, using 8 amp relays in place of a 2 amp relay. So here we go. So this is how this works. So the signal comes in from the AN2, and that will tell this thing to switch. Now, as mentioned earlier, this is relay B coil, and this is relay A coil. Now, I'll turn on my power supply here, and if the radio is defaulted to receiving and transmitting through the antenna A jack, the antenna B jack has to be grounded, and that's what this is doing right now. So if you press antenna B on the front of the Yaesu FT-1000, of course it's going to switch its action, and then of course now we've grounded antenna A, and antenna B is now letting the signal through, and that's really just how simple this circuit is. So you can see the switching action is nice and solid there. All these LEDs are doing is just indicating the action of the relay coil for, you know, basically video purposes here. And if you're building a circuit, you can actually use LEDs to be a little bit of a reference to yourself also. They work pretty well as test gear too. So that's, I think, another video within itself. So that's how this is going to work here. Now you're thinking, of course, this is reversed a logic action here. I could have done it the other way, and it probably would have simplified things. And then, of course, when the radio's turned off, both of the antenna ports would be grounded, and you know, there's a bunch of ups to that. Well, now we're dealing with the actual relay structure itself inside, and that's the reason that I went with this kind of reversed logic pattern. And when I come back, I have a dissected relay. I have enough of these relays, so I've dissected one of them, and I'll show you all the thought considerations that I've had before I've designed this circuit in order to make the best circuit possible. Alright, this is one of the relays that I'm using. This one is completely disassembled. It's seen better days, this one. This is the little arm inside of this relay that is on top of this coil, and of course this is just the relay put together. This is what it looks like when it hasn't been opened up. So, now this relay here is rated at 8 amps, and that's of course with this contact in here like so, and it's of course in its off state, so that that's connected to this upper contact here. Alright, the lower contact is rated at 10 amps because you have the tension of the actual coil itself pulling this arm down and putting tension on that contact, so we get about 10 amps of contact rating there, whereas, as I say, only 8 in the normally closed position. Now, the reason that I have this running in reversed logic is because this aperture here that's connected to this contact, there is no isolation in this aperture. So you can see this pin here on the back of the relay. Let's try and get this in the center of the screen here. This pin here runs right up through the back side here, and then this, of course, is connected directly to this arm, like so. Alright, and then that arm goes through, and then the signal comes out the other side. You'll notice that right below it, the magnetic aperture that pulls this arm in will make contact to this arm. So I'm going to deal with a piece of metal that's going directly in the middle of this coil here, and I don't want to have that in my RF path, and that's the reason that these are working in reverse. So when this relay is actuated, this arm is grounded. And when this relay is not actuated, of course this is floating, so this is up and it's not touching this metal aperture here, and it's making contact to the upper contact in the normally closed positions, and that's the position it will be carrying RF in. So that's one of the considerations, and this is kind of why you have to tear down relays. You have to know what's inside of them before you want to design with RF. It's not like designing something with DC or just, you know, low frequency AC like 60 cycles or something like that. Now, this piece of metal here that's the magnetic surface is isolated from this coil. There's quite a thick piece of plastic between here, so you wouldn't have to worry about any, at 100 watts or 150 watts, you wouldn't have to worry about any burn through or anything like that. But still, when this, if you have RF on this contact, when it's pulled in, that RF is not only going through this and coming out the contact on the other side, but it's also going right down the center of that metal aperture through the center of that coil bobbin, and we don't want that because that's going to add extra inductance at high frequencies, and it might cause a little bit of an SWR, probably going to get some reactance there. So we want to stay away from that, and I don't want to have to second guess this when I put this together. Don't want to experiment with that and find out how that's going to work. So it's better just to use it in the reverse state and just completely avoid that problem altogether. Now there's a bit of a gap, there's not a whole lot of a gap between this when it's in its normally closed position when this is up. So when this is up, of course, it's going to be further away from this little metal plate. If my finger was this metal aperture here, when it's up, of course, it's going to be away, right? So it's about the distance of a couple of sheets of paper. But, when that's really converted into picofarads, we're, dealing with very, very low capacitance. This is floating to begin with, so it's not really attached to anything, and it's insulated from the coil. So there's a bunch of bonuses in running the RF in the normally closed position of this relay. And that's the reason that you dissect a relay when you're going to use this in RF. So, of course, when you're building any kind of RF circuit, you kind of have to understand the way that it works and the way that different frequencies operate and stuff like that. And this is all stuff that has to come into play. So when you have a dark-coded relay like this could be put together any old way inside. You really just don't know. So you have to buy one as an experiment and destroy it. Now, if this was going to be running, 100 watts at, say, 3 megahertz only, I wouldn't be so concerned about that. But, our FT-1000 goes comfortably up to 29.9 megahertz, and, no problems. And that little bit of extra inductance in the center of that coil, and, of course, having this coil energized, and both of these coil pins are dragged to RF ground with capacitors, we're going to probably start to see some issues there. So that's the reason that that I've used this in kind of a reverse logic pattern. So next we'll take a look at the actual relay on an analyzer, and we'll look at the relay in its normally open position, because that's the position we're going to be using it in to pass RF. As I say, when it's closed, this lever will just be grounded, so it won't really matter. And we'll look at the relay and see how it responds to different frequencies. So we're now ready to see what this relay looks like at RF frequencies. And I've made a little mock circuit attached right to the relay as close as I can get to the contacts to mimic it when it's in the circuit board. Okay, so now the circuit board's still going to be better than this still yet, but if we get good results here, we can expect really good results when it's in the circuit board. So this is the same connector that's in the Yaesu on that antenna board. I have a 47 ohm dummy load across the relay here so that this is terminated to the contact here. And I've got two RF decoupling caps across the coil here attached just to the ground here. So I've got the corresponding connector right here on my MFJ analyzer, and I'll just plug this in and we'll take a look at this relay. So what we're looking for here is we want x equals 0, the lowest amount of reactance that we can get, and we want a standing wave ratio that's 1.0 to 1. And of course our resistance is what the resistance of the resistor is, so anywhere between this and 50 ohms would be absolutely great. So now this box is modified, my MFJ-259. I can take this right down into the kilohertz. Like right now we're at 521 kilohertz, and it's still fine down here, but that's pretty much telltale. If it's good at 1 or 2 megahertz, it's going to be good down here. Okay, so I'll go back up here again. We're at 2 megahertz, absolutely fine. Okay. We're at 4.7, absolutely fine, x equals 0, impedance 46 ohms, SWR, standing wave ratio is 1.0 to 1. We're at 11.9, still absolutely fine. Now we're at 30 megahertz, which is just above the top end of where the Yaesu goes, the FT-1000 goes. Now you can see our SWR is absolutely flat. We have X equals 2, so a little bit of reactance in there, and the resistance, or the impedance, is 50 ohms, okay? Now that's because this is hanging out in open air. So there's no strip line on this, there's no, it's not on a shielded pad or anything like that. So I can kind of mimic that a little bit by just pinching this against the machine and using the machine as kind of a ground plane, and you can see we get our response back again. So it's not really hanging in open air anymore. So if I go up to, say, 68 megahertz, we're still doing fine, completely flat. 1.0 to 1, X equals 0, and 51 ohms. This relay is really good to go. This is well beyond where this relay needs to be. So we can see here that everything is absolutely fine. We basically swept this relay and with a dummy load on one end of it, and the relay looks like a nice clean pipe for the RF to travel through. There are no kinks or bumps in it. And that's basically what SWR and all this other stuff does. If you have high SWR and stuff like that, there's bottlenecks somewhere, and there are no bottlenecks. The last thing we want to do is use the antenna tuner in the Yaesu FT-1000 to tune our circuit. That would be absolutely horrible. So I know now that these relays are very good, and I can use these relays in all sorts of different kinds of RF applications. And of course I will make a data sheet and put this with the relays, so next time I don't have to do this over again. I've just recently picked up these relays, and I picked up a whole tray of them, so I'm doing pretty good with some RF switching relays. So I'd done this before I started even with that schematic, or the actual little breadboarding circuit. I did this way before that, or before I even started on the circuit board or anything. It's the very first thing I did, because if this relay does not work good at RF frequencies, I don't want to design a circuit around it and then have it fail, and then of course I've done all that work for nothing. So this was one of the very first things I did, but now I'm just illustrating it to show you here that this is one of a very, very necessary procedure if you're going to make any kind of antenna switch with any kind of a relay. So now we'll go take a look at the layout and the schematic, and I'll show you how the actual circuit works. This is the new antenna switching circuit for the Yaesu FT-1000, and this is how it works. So say your radio is defaulted to antenna A, alright, so when you turn your radio on, it's in the antenna A position. Okay, you turn your radio on, this lead is low, this is AN2, this is low because this only goes high when you select antenna B. So this is low right now. As soon as you turn your radio on, 13 volts is present here. It goes up here into the coils of both of these relays. Also goes down here, turns this transistor on, and keeps this transistor off. So now that we're in antenna A position, alright, antenna B pulls to ground, and antenna A is left alone, and our path is through antenna A. Okay, so now we select antenna B. That means that this goes high. This BC817 pulls this low, this transistor shuts off, this transistor turns on, selects antenna A relay, pulls it down, okay? So now antenna A is grounded and antenna B is active. We can see the path is up through here and into antenna B. And that's just how simple this circuit works. So the circuit doesn't draw very much whatsoever, 34 milliamps, and there's always one relay on. When the relay's on, it'll either be B or A. And it's the relay coil current is extremely low, so the circuit itself hardly draws anything. It takes only 450 microamps at 5 volts to turn this on, which is basically factory for the stock circuit board in there. So everything on here is ready to go. This is the final schematic. I've added one extra 0.01 from here to ground, and there are a couple of more 0.01s probably added. These are just for RF decoupling, and you can never have too much of that. I don't want to have to go in here and search for any kind of RF issues, and these things are cheap enough, so I'll pepper them with RF decoupling caps, and that way it'll be good. So there's decoupling caps across the transistor and from base to ground on each one, and just to keep RF out of these places. So one thing I haven't illustrated in here is there's an inductor. They had a 1.4 microhenry inductor in there, and I will add this into the line. It's already added into my layout. I just don't have it illustrated here. So there will be one inductor here and an extra 0.01 to ground, if you could picture that off of this schematic here. And that's really how this works. Pretty straightforward. So this should be very dependable, and we've already looked at the relays. The relays are good to go. So we've got a good antenna switch in the making here. I finished the layout for the RF switching board, or the antenna board, in the Yaesu FT-1000, and this is what I came up with here. Of course, this is blown up on the screen quite a ways. It's really small and in real life, but this is blown up so that I can work on it. So now we'll see here the green layer is the top layer and the black layer is the bottom layer. This is where the two relays sit, here and here. This is where the RF jack is here, and this is where the signal comes in, right here. Okay, I'll just get rid of the bottom layer here, and this way we can see what's going on the top layer. So this here is where the signal comes in, alright, or goes out. This goes right up to the SO239 jacks. This is micro strip line, and it's tailored to be as close to 50 ohms as possible. Now the two SO239 jacks on the radio, great care was taken to keep these two mounting holes in the perfect spot, so these will go right underneath those two SO239 jacks. So when this board fits in, the SO239 jacks the center conductors will sit right on top of this strip line, and it will get soldered directly to it. And then of course the relay will select either to put that to ground or to feed this into this terminal here, which is the RF jack, which runs out to the inside the radio here. So we'll look at the bottom layer now. Get rid of this layer. So now we're on the bottom layer, and this is where all the components are. We can see here that we have more strip line here, micro strip line, and then on the top that's the ground plane for this one. The signal comes in the jack here and is dead center, and this is again 50 ohms, so cut as close to stay at the 50 ohm impedance as possible. This here is as I say, signal in or signal out to the radio, and then this here again is running up to the two SO239s. This is AN2. This signal is what tells this little transistor right up here whether to turn this relay on or to turn this relay on. This is the PNP transistor here, and this is the NPN transistor here that controls the coils, will drag the coil to ground. Either one will. So this is the choke that I didn't add in on the schematic. It's a 1.4 microhenry choke here. I'll just show you what the choke looks like. That's the little choke here. I don't know if it'll focus in on my hand. There it is. Alright, that's the little 1.4 microhenry choke that I'll just solder right on there like so. Alright, and that will fit right here. All of these are 0.01 mic decoupling caps. RF decoupling caps are everywhere. You can see they're all 0805 parts. These are 1206, these ones here. So the signal goes in here through the 10K resistor. Up into here there's a 47K to ground, and right into the base of this BC817. Alright, and then we have on the PNP there's a 1K resistor across here, and then there's a 22K resistor across here to this BC817. This is the 807. This is the 817 here. And these are the two diodes. These are snubber diodes across the coil, and it's relatively simple. It's almost pretty much done at that point. So I do the toner transfer method with my printer, and I'll put this circuit board together, do the sandwich thing. So I have the top layer, and then I align them on a Fresnel lens. I have a light shining through a Fresnel lens, and I line both layers on that. And then I slide the circuit board in between them and stick them through my special laminator to make these circuit boards, and that's how I get my circuit boards. So I'll do that step next and populate this, and we'll try it out in the radio and see how it works. The PC board is done. I haven't populated it yet, but I'm just laying it in the chassis to see if everything lines up, and it looks like everything is pretty much spot on. You can see where the SO239s are just going to solder directly to the microstrip line here. And if I shut the lights off, you can kind of see the hole centers are pretty much absolutely perfect there. So it just bolts to the existing areas, and then of course it'll have a little bit more support because it'll be soldered directly to these jacks here. So the next job is to populate this board. I'm now ready to populate this board, and usually what I do is I work this way. So what I do is I pick the component up in the tweezers like so, and I'll put them on the pads, and of course I use some RA flux, so I'll dab some RA flux on there, and then I come in with the soldering iron and I work this way. So I usually work this way here, I'll work this way, and if I have components that mount the other way, I'll just rotate the board because it's much easier to work like this. So I'll zoom out here. You can kind of see I'm sitting here, so when I'm working it's much easier to come in like this than it is to kind of go like this, right? So that's what I do, and then as I say, if I have to mount any components like this, I'll work this way. So the light's kind of making it really bright there, so you can kind of see I'm working like so. So what I'll do is I'll populate this board, I'll put all the components on it, and then we'll try it out, see how it works. The new antenna switching board for the Yaesu FT-1000 is now fully populated. You can see the switching transistors here, and the 1206 resistors here. This is that 1.4 microhenry choke. These are the diodes across the coils of the relays. They don't really need to be this big, it's just that I have so many of them, I figured I'd use some of them up. These are the RF bypassing caps, all over the place here, kind of peppered with them. That's the underside, and then of course on the top, I installed the jack out of the other board so that the radio will just plug into this with ease. And you can see the little RF jack here. This little RF jack is, I've got a bunch of these, so I just put another one in. I left the old one in the old circuit board. So you can see the difference in the boards here. This jack runs off sideways. This one here runs this way, but there's so much cable it really doesn't matter. It can come around the corner and there's still a lot to spare. So I did that, of course, to keep it in the center here so that there's equal length to each relay. And this is pretty much, it's moved over just a little bit, but again, there's lots of wire there, so I'm not really too worried about it. So I'll probably solder a ground to this portion here from the back of the radio. Of course, this is the strip line that'll be right underneath the SO239s there. So I'll see how that goes. But that's the new board, and it's now ready for installation. The new antenna switching board is now installed. It worked out quite nicely. Everything fit just perfectly. These screws went in nicely, and the micro strip line is lined up perfectly with the SO239 jacks. So you can see that the wiring here still isn't tidied up, and that's because the final amplifier and low pass filter unit is still upside down, and I kind of need this extra loose wire here in order to move it around. So no RF is fed through this. It's ready to get tested in the end, and we'll go through and make some performance checks on this in the end. But first, I'll explain what I've done here, and I'll also show you how to set up the 2SC2879s, the RF final amplifier's idling current. Alright, so this section here has all been tested, all the relays have been tested, everything's fine. I've gone through here, tightened up all the screws, loomed the wires properly, got things tied up in this area. So everything in this area here is A-OK, ready to go. The low pass filter unit, absolutely fine. This is done. This amplifier here was a lot of work just because it was so messed up. So I had to spend a lot of time in here, a lot more time in here than I spent in here, that's for sure. So where do I start? We'll start with the thermistor. Okay, remember in the beginning video, remember how the thermistor was kind of sprung up? Well, obviously it can't sense temperature that way, and of course the thermal goo is let go and everything there. So the goo doesn't actually hold it down, it just sits there, and then this stuff sits in this. It's actually a putty, a thermal putty that it sits in. And I'll explain all that here quite shortly. So if your thermistor is sticking up, or if you have to test it, because this one here is what turns the fan on and off, this water wheel or paddle wheel or squirrel cage or whatever you want to call it, this little fan here, that thermistor there is what turns this on. So if this guy is not sensing temperature, or if it's not pressed right against the ceramic case of that 2SC2879, it's not going to sense temperature properly, because you got to remember, heat rises. This thing is actually upside down, so that thermistor is hanging down as heat's rising, so it's not going to turn on correctly. And that's why there has to be that thermal putty between the two components. So if yours is lifted up, or if you had to lift it up to test it, and the same goes for the diodes that go across the cases of the TO220 style transistors here. How you retension that down is very simple. Of course, there's no power on the radio at this time. What you do is you push your finger down on the thermistor package, push it right onto the body of the 2SC2879, of course, and of course there's new thermal putty on at this time, right? So you're going to get a little bit on your fingers. So you're pressing this down against the package. Get an insulated tool of some sort. Of course, there's no power in here anyways, but you still want to do that. Plastic tools are a little bit more gentle on things. Push down on it so there's tension between the thermistor and the body of the transistor. Stick this under the legs of the thermistor and pry the legs up just a little bit. Of course, using common sense, you're not going to pry the legs off the circuit board or pull them out of the thermistor, but you're just going to bend them up a little bit, and that'll put some down pressure spring tension on the thermistor, and the thermistor will then stay against the body of the 2SC2879. So you won't have to worry about it. It'll keep itself pressed there. And that's what you need to do. So make sure, as I say, the thermal putty's on first, because if you go trying to shove thermal putty under there, you're going to lift it up again. Okay? Same goes for the diodes. Push the diodes against the body of the transistor and lift the legs just a little bit on each side. Again, using common sense. Don't pull them off the board or out of the diode. And then once you're done, let your finger off and there'll be down tension on that diode pressing against the body. So this thermal putty, there's a bunch of different kinds of thermal putty, and you need to make sure that you have the right stuff. Alright, if you don't, you want to be very careful about saving the stuff that's in here, because the stuff that's really common is really runny. And you can't use that for this. This stuff is designed to stay gooped on the top of these transistors and stay there. If you use the runny stuff, when the transistors get hot or the amp gets hot, it's going to get soft and drip into the lid. So you got to remember, again, this is upside down, right? So it's going to drip into the lid, and you won't have very good thermal conductivity between the components on the top of the transistors and the transistor. So you want to save that stuff. If you find that it's dry and it's chunky, if you have some of the more the wet stuff that doesn't have a very thick consistency, I guess you could almost call it the normal thermal compound, take just a very little bit, and I'm talking not very much at all, just the littlest amount of your fresh thermal compound, and mix it in with the old stuff, and like magic, this stuff will just, it almost liquefies it again, and it comes right back to life again. So that's what you want to do. Use very little of the new stuff, the runny stuff, and mix it in with the old cakey stuff or the putty style stuff, and remix it up and use it over again. Make sure that there's no solder balls or any kind of chunks in it, and make sure that it's all clean, and you're off again. Everything's working good that way. So I had to desolder all these transistors and move the legs apart, because the legs that were soldered onto the pad, some of them were almost shorting over the pads to each other. Yikes. So I had to unsolder all this, desolder them all, and clean off between the legs with acetone I used to clean off the resin, the leftover resin. You want to make sure the resin is gone between those legs. As I say, if there's any little splattery solder balls left behind, they could cause a future short. So that was all done in this section here. I resoldered the base connections to these 2SC2879s and cleaned around them. The resin that you see on here is still from Yaesu. That's their factory stuff, and that's absolutely fine. It's not overlaying anything. It's fine to be left on there. Resoldered a transistor down in here. All the screws on the board after this point are completely retightened. Everything is cinched down. Even the 2SC2879s, I tightened their cases to the board. What else can I tell you here? This screw was stripped on the positive lead, and I have a good idea why, because a lot of people do this and it's a misconception. They think that you can remove the positive lead to the amplifier and set the idling or the idle current to these 2SC2879s by putting your current meter in line with this and here, because a lot of people don't have soldering irons, or maybe they just don't want to open this connection. I really don't know why they do that at this point. But you can absolutely not set it like that, because this is not just setting the idle current for the two SC2879s. If you remove this screw here, this is setting the whole entire board. So you're going to have quite a bit of current draw there, and then you'll be adding the idle current on top of that. So you'll have a pretty high current setting at that point. If you turn down the idle current, you probably won't be able to zero it out, because the rest of the board is powered up at this point. So you definitely have to remove this jumper to do that, and this positive has to stay there. So I have the old screw here. I don't know if you can see that. It's focused in on my hand here. See, the threads are all missing right in here. So this is that's usually the only reason that you remove that screw. It's a common misconception in these, is you can remove the positive lead, but you just can't do that. So this connection just breaks the collectors, and that's all it does. It breaks the collectors to the 2SC2879s. So when you open this, the rest of the board is still powered up. If you open this, it's just the collectors to these two transistors are completely open at that point. So what you got to do is make sure you have an isolated current meter, okay, and then hook your current meter across this once you've removed that jumper. Now, before you remove this jumper, you have to have no power in this radio whatsoever. This is very important. Nothing is hooked up to this radio. No coaxes, no microphones, no patch cables on the back of any sort. For reasons being is if you have any ground isolation problems between your soldering iron and the chassis of this radio, you're going to cause a lot of damage. And there's no point in even taking any chances. Completely floating this chassis. Sitting on a wooden bench and it's not touching anything metal. There's completely floating this chassis. At that point, desolder the jumper, put your current meter in line. Your current meter is isolated also from the AC line. And at that point, what you can do is make sure that the MOX button is not pressed in, so it's in receive mode when you turn the radio on, okay? Plug your radio back in, turn the power on. Your radio should just be in receive mode at this time, and you should register absolutely no current on this current meter here, okay? Alright, just a quick note here. This is the VR that we're going to be adjusting. This little VR here sets the idle current to the final amplifiers right here, okay? So you're going to be looking at your meter. It's going to read this. There's going to be no current there, okay? Alright, so now with no current on that meter, what you're going to do is on the face of your Yaesu FT-1000, you're going to put it either into lower sideband or upper sideband. I have this one in lower sideband. There is no microphone hooked up. The mic gain is turned right down to nothing. The RF power is turned right down to nothing. And now you're ready to set the current, the idling current on those two SC2879s. Okay, so now what you do is you put your finger on the MOX control with your current meter in line, you press the MOX button in, and you'll see the current do this. And you're wondering, well, why is it moving around so much? Well, that's due to temperature change. That diode on the top of that transistor is sensing temperature, and of course there is a little bit of variation in the transistor itself, so things are going to move around a bit. It's very sensitive to temperature, and that's what that diode's job is. So you're going to see it move around here. Alright, see how it's quite cold? So now, if I blow on this, watch what happens if I just blow on the tops of those two SC2879s. That's it. See how sensitive that is? So I'll just put it into MOX mode here, or take it back into receive. And I'll let it set for a second. So what you got to do is you can't be too finicky with this setting. The rating for this, okay, is 400 milliamps. You set that VR to 400 milliamps, positive or negative 50 milliamps. So what they're telling you is set it to 400 and it's going to move positive or negative 50. And that's just a comfortable zone. You want this to be at room temperature when you're setting this because it will really affect this setting. So, and it's, as I say, it's extremely important to do that. All right. So with this thing at room temperature and it's been sitting for a while, alright, if you first turn this on and find out that it's around 800 milliamps or something, or an amp or over an amp or something crazy like that, immediately turn that VR down to 400 and then let it settle off and then shut the thing off again, shut the thing back off. The MOX button is now back into receive, okay? And let it sit in receive for a minute and then turn it back on and see where it sits, and then once you kind of get it comfortable, set it around 400 milliamps, and it should be fine. As I say, don't get too finicky because it's going to move around a little bit. So I'll put this back into MOX mode again, and we can see it climbing up. So what I'm going to do is I'm going to let this settle off for about 15 seconds, okay? So we'll sit here and we'll let it count up. You will note that with these particular amplifiers, that diode is going to compensate quite a bit for a, if you warm the actual diode up and warm the package up, the current will actually go down. So that's how it's intended to operate. If I heat that with a heat gun, the current will go to 300 to 200 milliamps, it'll go down. So that's actually how it works, and that's designed to protect those transistors when they get very, very hot. It's just downing the current. So, at any rate, so here it is. It's kind of settling off. So I can keep lighting this. Will probably settle off around 400 mils. I probably don't even need to set this. I've preset this before. When I first turned it on, it was sitting at about 700 milliamps. So I dropped it down, and I'm just going to see how far it takes to, how long it takes to settle off. I could move it around. I'll move it around and just give you an example, okay? So I'll stick my screwdriver in that little VR now. You can see we can bring it way up. It was up at 700, right? So it doesn't need to be down there, and of course it'll go way down too, right? So what we want to do is just set this to 400. Alright. So there it is. So we have it set at 400. Now I'll just put it back into standby mode here again, so it's actually receive. When you turn the, depress the MOX button and the MOX button is out, it's back into receive. So the amplifier itself is in a standby mode right now, and that's set up by that wire that was disconnected in that TRV circuit that I explained earlier. So I'll just let this sit for a second. And then in a second here, we'll turn it on again, let it settle off, set it one more time, and at that point, we're done. And that's really how generic this setting is, because it's just going to move around a lot. Okay, so I'll turn it back on. And we can see that we're pretty much going to be within the zone right now. So I really don't think that we're going to need to reset this. There we go. So it's settling off around 400. It'll probably still count up a bit. There you go. See, so it's going to still count up a little. So I'm still, 400, it's positive negative 50 when it's been sitting for a few. That's absolutely fine. As I say, don't get too finicky with this because it's just going to move around a lot. And don't set this if you've just taken it out of a garage, or it's been sitting in your car, or it's been in some sort of extreme heat application or something like that. You want this at room temperature. And set it, and you're pretty good at that point. And that pretty much finishes off the finals idle set there. So after this point, disconnect the entire radio again. All right, the chassis is floating like I explained earlier. Resolder that jumper in here again, and turn this thing, put the lid back on, turn it upside down, and it's ready to go. So as I mentioned earlier, if you turn this thing on and you find out that the current is incredibly high, right off the, as soon as you turn it on, it's at 800, 900 milliamps. Immediately go in here and turn this down to 400, and then let it count for a little while. All right, as long as it doesn't drift too far from 400, put it back into standby mode, or back into, depress the MOX button so it's back into receive mode. The radio's in receive. This is in standby mode. Okay. And let it sit, and then turn it back on again, and then of course do one final check and set it up to 400. If it's not wandering too much like this one, use what was here as an example. If it's not wandering too much, you're fine at that point. And that's it. That's pretty much it. So I'm just going to put this thing back together. I'm going to loom up some wires here. Once all the wiring is completely loomed up and this thing is together, I've got this, the squirrel cage or water wheel or whatever you want to call it, fan back in the case here. We're going to be absolutely fine and ready to test out the new antenna switching circuit and see what we've come up with at that point. And that's what we'll do next. Just a quick note on the reassembly of the low-pass filter unit / RF output amplifier unit in a Yaesu FT-1000MP. When I got this, all these wires were out on the inside of the box, including the coaxial cables here. They all came out this one little plastic grommet / little hole here. Some of them were on top of the hole. And it never did really feel right, because I noticed when I took it apart, there's a bit of a bubble in the lid here. I didn't give it much thought, because the lid came off with ease, and this screw was finger tight when I got it, so I just unscrewed it, and it came apart, and I started looking in the amplifier, and was horrified by what I saw. So I quickly lost thought of this, the cover for the RF amplifier / low-pass filter unit. Now, upon reassembly, I was never really comfortable with running these wires past the low-pass filter unit and everything. It just didn't feel right. So I'm putting this thing back together. The lid's not fitting on quite right. These cables are kind of buckling in here. They're on a 90-degree angle, and it's just something's not right here. I noticed that there was a piece of tape here from factory Yaesu tape with a piece of tear, or with a tear in it. So something's really odd here. So it would only make sense that these are unshielded wires, and they want these outside the box as soon as possible. So this wire runs through that piece of tape that had a tear. I guess somebody had torn the wires out of the tape there, and reroute them inside the box. Same with these wires here. They want them out of the box as soon as possible, so the connector's right here. It comes right out here. There's a partition in the box to keep the RF amplifier separate from the low-pass filter unit. And of course, these things were bent on a 90-degree angle, buckling this. Well, there's square cutouts here, and these are supposed to be plugged in through the actual shield here. Another good clue to that was this cutout here. We notice the cutout sits here. Right, and look at that. These cables come straight out in this little cutout in this bracket here. This bracket holds the RF amplifier unit into the area there. So the only wires that are supposed to actually come out over in this side of the unit really are, this is the RF drive wire. It goes through this little grommet here, And this is the positive and negative supply leads for the RF amplifier, and then these are the fan wires, the fan circuit wires. They run off to the regulator board, and then right in front of the connector on the regulator board here, right in front of this connector where it plugs in, is where the fan plugs in. So that's how it's supposed to be done. So if you are having problems reassembling your Yaesu FT-1000, or it's been assembled incorrectly, this is the correct way to put it back together. The Yaesu FT-1000 is now put back together, and I'm pretty much ready to do some testing. You see that the squirrel cage moves nice and free now. No noises. Wires are loomed up properly. You can see all of the wire ties on here. Everything's all put back together. I've undone the cable from the radio to the antenna switchboard because that's what we need to test. So you can see back here how the SO239s are kind of soldered in. I've got this wire tied to it, so it's pulling on it a bit. You can see how those are tied in there, soldered to the strip line. So that board is pretty much ready to test. The radio is going to control this board, so basically I'm just going to use the AB switch on the front of the radio to move the relays back and forth, and we'll test their action. So we'll do that when I got my camera back on the tripod here. I'm now ready to test the functionality of the antenna switching circuit. So the radio is in antenna B, the radio's on right now, and it's selecting antenna B. So that means that antenna B should be connected to the center conductor and antenna A should be grounded. So let's just test that right now. So we got antenna A. You can see that's grounded. Okay. Now we'll test antenna B, and it shouldn't be grounded. It's not grounded. Now it should be making, the center conductor here should be making connection to the center conductor in this little RF jack. And we can see it is. And of course it's not shorted there. So so far we're doing good. So I'll select antenna A now. Get onto here. Okay. So now antenna B should be grounded. And antenna A should be connected to this jack in here. No problems. So we're pretty much ready to do some SWR and all sorts of tests on this with the analyzer. I now have my analyzer hooked up to the antenna switching circuit in this Yaesu FT-1000, and we're ready to look at it and see how it performs. So I'm just going to go in coarse steps here. I'm not going to, really sweep every frequency because we'd be here for a long time. So I'll just go in coarse steps, and that's good enough. That'll tell us how well this thing actually works. So that 47 ohm resistor that was on the relay, I now have in a PL259 connector, and I will put that on the back of the radio because I have to attach the resistor somehow to that SO239 jack. The radio is on, so I can switch between antenna jacks here. You'll hear it. Alright, so it's switching between the jacks right now. Right now I'm on antenna A jack, so I'll screw this load onto antenna A jack. Okay, there we go. So we're at 1.88 megahertz, resistance 47, X equals 0, 1.0 to 1. Absolutely fine. You see the resistors on the verge of 46, 47 ohms. Okay, we'll go to 4.4 megahertz, same thing. S standing wave ratio, SWR, 1.0 to 1, X equals 0. Can't ask for anything better. 11.129 megahertz, resistance, or the impedance, they call it resistance here, our impedance is 47 ohms, X equals 0, 1.0 to 1. 28.5 megahertz, same thing. Now let's go right out of the range of where this switch even needs to go. Let's go right up to 66 megahertz. Look at that. 1.0 to 1 SWR, X equals 0. Impedance 46 ohms. Okay. Now let's go right up to the VHF region and see what we get. 1.0 to 1, X equals 0, and about 51 or 52 ohms. And that could be a bunch of different things in the circuit. It could be the length in the relay or this cable. I don't know if this cable is even good up to this frequency. It came out of an old HF rig. It happened to have the same connector on it, so I was doing pretty good. So there's no point even looking up here anyways because it only goes to 29 megahertz. And if we can make it comfortably to 66 with no problems, I can say, pretty comfortably that this is going to be just absolutely fine. So we'll go back down to the bottom again, and I'll select antenna B, so you'll see this. You see it just opens up. because this jack is now open, so I will put in an antenna B jack. Alright, looking pretty much the same. Impedance 47 ohms, x equals 0, 1.0 to 1. You can see the screen, I'll just move it up. 4.4 megahertz, 11.12 megahertz, 28.5, 66.7, and 116 megahertz. Looks like we're doing pretty good at this point. I would call this antenna board, this antenna switchboard, an absolute success. So now what we're going to do is the final test. We're going to put some RF power through this and we'll look at it on the Marconi analyzer. I'm now ready to test the new antenna switchboard in this Yaesu FT-1000MP. You can see it's all hooked up and ready to go. This is the cable coming from the radio going back into the board here again, and we're on antenna A port, so this relay right here is going to be passing the power out to the Marconi 2955B analyzer, which has a 50 ohm dummy load inside it. So here we go. The radio's at 3.8 megahertz. It's in the CW mode, so all I really have to do is push the MOX button and turn up the RF power. So let's give it a shot. Here we go. Alright, I'll turn it up. 101 watts. I think we gained a watt. And I'll do it one more time. 101 watts. Doing good. So now I'll bring it up to 29.5 megahertz. And we'll try it again. 106 watts up at 29.5 megahertz. Doing real good up here. And I'll turn it up one more time. 106 watts. No problems there. SWR is completely flat. So I'll move this over to the antenna B position. And we'll test the antenna B side. Alright, antenna B. Here we go. Still at 29.5. 106 watts, no problems. So let's go down to 3.5 megahertz, or 3.8 it was, 3.8 megahertz. And I'll put it back on antenna B, because it remembers antenna A down here. And let's give it a shot. 101 watts. And of course the SWR is completely flat. So it looks like this antenna switchboard is a winner. Well, the radio's now finished.
I get looking at the control carrier modulation and those things.
So I talked with these guys for quite a while this morning, and they say the radio sounds really good. I haven't been on the air now for about 45 minutes or something like that, so these guys are still going on about something. They're talking about controlled carriers. But it works very well. I also made some sideband contacts. Everybody gives this thing glowing reports. So of course I have my own monitoring equipment. I can listen to this myself while I'm setting it up and aligning it and doing all this kind of stuff. So, but it's always nice in the end to get, you know, the final result, talk to somebody on the air and see what they have to say about it. And it was all really, really positive. So I think it's about time for this radio to go back to its owner and make the owner happy. So I hope you enjoyed following along through this entire repair process and modification process. If you did, give it a big thumbs up and hang around. There will be more like this in the near future. Just hopefully not as in depth as this one was. This one sure took a long time. See you next time.